Hello everyone, I'm Ashwin Kulkarni. Welcome you all in this quantum computing series. So I hope all of you are doing well and learning something new every day for sure. So let's get started today with something new and something important for the further set of videos in this series. So today let's get started with a quantum circuit. So today I'm giving you the basic idea about the quantum circuit and how it looks like. Of course, don't get scared by the different symbols or different notations or the figure that you are going to see, because we are going to learn that bit by bit in upcoming videos. But today I'll just correlate one particular quantum circuit with a one particular classical circuit, so that at least you will get some idea that yes, we can build something which is similar to classical computers in quantum computers as well. So as you can see on the screen, I have shown you one circuit which is a classical computer circuit which is called as half adder. So what half adder does is it just adds two binary bits and just output in the form of sum and carry. So when you add two binary bits at 0 and 0, your sum is going to be 0, of course, and carry will be 0. When you are going to add 0, 1, then your sum will be 1, but carry will be 0, right? And similar in case of 1 and 0. And when you are going to add two ones, that is 1 plus 1, so it will essentially, in case of binary, it will so in case of normal base 10 system, it will generate a 2, but in case of binary, what it will represent is sum equal to 0 but carry equal to 1. So because this is in base 2 format, that's why this your sum will be 0 and carry will be forwarded as well. Now in our classical computers, how do we basically how do we construct this particular circuit is by using XOR and AND. So there are different ways as well, but the simplest form to construct this particular circuit is using XOR and AND. Now you might be able to recall these two gates in our classical computers, but again I'll just quickly tell you what these gates do. So a particular AND gate will output as 1 only if both of its input is 1, right? So AND gate output will be 1 if both of its inputs are 1. Of course, these are binary gates. Now your XOR gate output is 1 if either of bits are 1. So either of input bits should be 1 and the other one should be 0. And if both bits are same, such as 0 0 or 1 1, then it will output as 0. So a simple definition of XOR gate is, if your input bits are different, then it will output as 1. If your input bits are same, then your output will be 0. That's it. Now how these two gates are correlating with the half adder is, so if you can see, to get a carry as 1, you should have both the input gates should be 1. So here you can see, if your both gates are 1, then only your carry is going to be 1. And similarly, when you can see in this particular table, if your both gates are same, such as 0 0 and 1 1, then your sum is going to be 0 and 0. And your both gates are different, such as 0 1 1 0, then your output is 1 1. So that's how we are able to generate a half adder, right? Now I hope you have understood. This is very simple and we all have already got over this. Now moving on to the quantum computer, similar for this particular functionality. Now of course you are going to see all these new stuff in this particular diagram, right? But consider it, I'm just correlating it with the above classical computer. Now consider this. So in this particular quantum circuit, you have Q0, Q1, Q2, Q3, and the last one is check, which is a major. Now there are 4 qubits, which are Q0, Q1, Q2, Q3. I have already explained what is qubit. You can go ahead and check out that particular video. Now, there are different gates are there. So one is C naught gate. So these two are C naught gate, right? So what C naught gate does, and what its functionality, I'll of course uh, I'm going to explain you in upcoming videos. But consider these two gates as C naught gates. Now, here you can see these two CNOT gates are dependent on the two qubits. So first one, so I'm considering this as CNOT 1, and this one is CNOT 2. Now CNOT 1 is dependent on Q0 and Q2, and CNOT 2 is dependent on Q1 and Q2. So these are two qubit gates. Now you can see there is third one, which is almost similar to the first two, but this is called as Toffoli gate. So this gate is called as Toffoli gate. So what it does is, the difference between C0 and Toffoli is, since C0 is 2 qubit gate, Toffoli is 3 qubit gate. You can see here this Toffoli gate is dependent on Q0, Q1, and Q3. So Toffoli gate is dependent on Q0, Q1, and Q3, right? Now, C naught is dependent on Q1 and Q2, and C0 is dependent on Q0 and Q2. Now, what is the significance of this gate, and what is its respective matrix and all that stuff? I'm going to explain it later, but a simple definition of a C naught gate is, so consider your first bit as control bit, and this bit as your target qubit. Okay, so when control qubit is set as 1, it will flip the state of target qubit. That is how C0 works. For example, if you are Q0, so I'm just going to explain a simple C0 on Q0 and Q2, right? Now, if your Q0 is 0, okay, then, and your Q2 is 0, then what is the output state? Let's say output state of Q2 means, so if your Q0 is 0 and Q2 is 0, then your output Q2 will be 0, because your control, so this is your control and this is your target. Your control is not set to 1. Now if you are, again, Q0 is 0, Q2 is 1, then your target is still 0, because your control, sorry, your target will stay as it is, because your control gate is not set to 1. Now, when your control gate is set to 1 and your Q2 is 0, then your output will be 1. So why is that? Because your control gate is 1, then the target gate will get flipped and it will be 1. And similarly, when it is 1 and 1, then your output is 0. So similarly, here, what you can see here is, when your Q0 as your control bit is 1, which is set as on, then your target qubit will get flipped. The state of target qubit will get flipped, which is 0. Now, you can simply correlate this particular table with this one, sum. So essentially, your CNOT gate works as XOR gate in classical computer. We can just, I mean, this is a very vague correlation, but yes, the output table looks same. Now, similarly, for second CNOT gate, so this is for CNOT 1. Now for CNOT 2, which involves Q1, Q2, and Q2, the similarly 0, 0, 0, 1, 1, 0, and 1, 1, which will be 0, 1, 1, 0, right? And now you have one more gate, which is Toffoli. So what basically here Toffoli involves is Q0, Q1, and Q3, right? So Q0, Q1, Q3, and your Q3. Now, similarly, if you are able to just think on it, okay? If your CNOT gate is 2 qubit gate which is dependent on one control and one target qubit, right? Now your TOEFL is 3 qubit gate which is dependent on two control bits and one target bit. So here two control bits are Q0 and Q1 and a target bit is Q3, right? Now we just correlate it with C naught. For the definition is same. When your control bit is set as 1. Now here compared to C naught in the TOEFL, when your both control bits are set as 1, then only your target bit will get flipped. That's how it is. For example, I'm not going with all 8 possibilities. I'm just going with the variation property. So variation possibility. So if your Q0 and Q1 is 1 and Q3 is 0, then your output will be 1 because your both control bits. So here this is control, and this is target. Both control bits set as 1, then only your target qubit will get flipped. Now if it is 1, 1 and 1, then it will be 0. That's it. Now here I'm not going into how you can flip the state of qubit. We'll go into that later. For example, now let's just set everything to 0. Initially, all your Q0, Q1, Q2, Q3 set to 0, right? Now, here, your C0, so it will pass to C0 1. So this is 0. Now, Q2 is already your control bit is 0, so your target bit will be 0. Now your Q1, here it is still 0 and 0. Now both your Q0 and Q1 are 0, 0. Hence your Q3 is still 0. So these are measurement gates. Of course, we are not going into it. Just think it that on this particular line, you will get your sum. And on this particular line you will get your carry, and we are going to measure it on C. Now here your of course your sum is 0 and carry is 0. Now consider second scenario. Okay. So now the second so consider it like this. Okay. Now say a second scenario is when your Q0 is 0, Q1 is 1, right? So this is essentially, this is your A, this is your B. So A is 0, B is 1. Now your output sum should be 1, but carry should be 0. Similarly, so this is 0, this is 0 is fine. Now when this is 1, right, and this is 1, your initial state of this Q2 and Q2 is 0, but your control bit for Q2 is 1, hence it should get flipped, right? Initially it was 0, it is now 1. And again this will be 0. So in this case, your sum is 1 and carry 0, right? Similarly, I'll just quickly take one case. So when your these both is 1. Now similarly, if your control bit is 1, then your target qubit will get flipped as 1, right? Because initially it is 0 and now this gets flipped to 1, right? Now here, now your Q1 is 1. Q1 is also 1. We have already set it. Now your target qubit, which is Q2, it is not 0 now because it has already changed to 1 here. So it will get again flipped to 0. Because your control bit is 1, so your target bit should get flipped, which was already 1, so it will get flipped to 0. So in this case, your sum is 0, but now how Q3 will work is, see, both of your control bit for TOEFL gate are 1 and 1 now. So this is 1, this is 1, hence its target qubit will get flipped to 1 and your carry is going to be 1. So this is how in 1 case you will see a carry equal to 1 and sum equal to 0, right? So this is how your particular quantum circuit can run. A particular quantum circuit for half adder can work, and you can construct this. So this is it for today's video. I hope you have got a spice of it, how quantum circuits are going to work, and there are different kinds of gates in it. We are going to look into it in further videos. Thanks for watching this video. I hope you like it, and just subscribe to my channel and share it with your friends. Bye.